Hello everyone and welcome back. Today we're going to be solving the popular system design interview question of designing a system to find the top K heavy hitters within a stream of data. Now this could be the top K most played songs on Spotify, it could be the top K most viewed videos on YouTube, it could be a dozen other things that you might be able to think of, but today we're going to be sticking with this example of top K songs on Spotify. It doesn't really matter though. The design will ultimately be similar regardless. And by the way, you can check out the full written version that this video is based on System Design School. It's completely free. It goes over a lot of background knowledge that you'll find useful, a lot of like sliding window kind of definitions, and a lot of background on stream processing. And there's also a pro course, like a premium course on System Design School that you can also check out. And this is one of the example lessons here. And you can see it's actually very, very thorough. It goes over a lot of things that most people aren't super familiar with. So it's, I think, worth your time to at least check it out. So let's not waste any time and let's just dive right into our framework that we have down here. Our 4 steps, which some can kind of be split up, but we'll start with number 1, gathering the requirements, the functional requirements and the non-functional requirements. Let's start with functional because those are kind of the most important. And in this problem, I think it's pretty obvious what the requirement is. We just want the top K songs, but it's not that simple. Well, what is top K? What's K in the first place? So let's say that K could be somewhere between 100 to 1,000. I think that's pretty reasonable. So we'll only return the top 1,000 at most. I think the second question is, what do we even mean by the top K most played songs? Over what time period? Do we just mean like all time? Or do we mean like within the last month, within the last week? Well, let's say we want to support a few time windows. Let's say we want to support the all-time window and we want to support at least a few or at least one non-all-time window. So it could be like the last month, it could be the last hour, it could be some other granularity, but we want to be able to support a window that does not include the all-time. Now, we're not going to have any windows that are like arbitrary. What I mean by that is if you imagine this is like our time, we're not going to be taking like a window of that. We're always going to be having a window from like the current time. It's going to be kind of grounded on that. That's what I mean by last month or last hour. So every window would have to like start over here. Those are the 2 main functional requirements. In terms of non-functional requirements, I think a good few questions to wonder would be how many songs are we actually thinking about here? So in the context of our design, that would correspond to the number of events that we're getting. So how many songs are being played? Let's say we're having 10 billion songs played per day. Okay, well, how many songs are there in the first place? Because, I mean, K is 1,000. If we only have like 10,000 songs, then this problem becomes pretty trivial. But we're not going to have that. As you can imagine, Spotify has a lot more than 10,000 or 10,000. Let's say we have something like 100 million, and I don't know how reasonable that is. I wonder if there are actually that many songs in the world, but for the purpose of our design, we will assume that this is how many total songs we have. It's becoming pretty obvious that we're probably not going to be able to solve this problem with a like single host solution. Probably going to need to do some horizontal scaling at some point. And let's say we want our results very quickly. So we want the latency to be, let's say 100 milliseconds to fetch the top K songs. That tells me that we probably won't be able to do some kind of massive batch job to like process all the data on demand when somebody makes a request, because if we have to do that every single time, it's probably not going to happen in 100 milliseconds, aggregating all of that data. Even if you were to use some kind of distributed data processing tool like Spark or Flink, probably wouldn't be sufficient. But anyways, the last requirement I'm going to have is the latency for a song play to actually count, or let's say to be included. So how long after a song is played before it's actually included within our count for our top K ranking? Let's set that to something like a minute. So we've got a decent set of functional and non-functional requirements. Let's move on to the API design, which is going to be pretty quick in this problem. It's really just going to be one get endpoint. So let's say it's something like top K. And let's say we have a couple query parameters for K, and maybe it's 1,000 here. And let's say the other one is our window. And let's say that is last month. Actually, we could probably word this better. Let's say 1M for 1 month. So nothing fancy here. This is not obviously where the complexity is within our design. In terms of like the database design as well, in this problem, that's not really going to be the complicated part. I mean, I think it is a little bit obvious that probably at some point we'd want to store the counts of like the songs played. So for each song, we want to know how many times it's been played. But other than that, there's not a lot of schema design for us to do. So now let's move over to the high level design. Let's try to create a working solution. It doesn't necessarily have to be scalable. It doesn't necessarily have to satisfy every requirement, but something that does work. And let's start with the all-time time period. Let's try to make things simple for us. We don't know how to solve the problem right now. Unless you automatically know what the solution is, you have to go through the steps and then kind of work backwards. So let's start simple and see where we end up. Now, the first thing I guess to talk about in our high-level design is probably like the streaming events. So we know that every time a song is played, some event will be produced and will be sent, and we want to consume those events. So we're going to make the intelligent decision of using a message queue / message broker called Kafka here. And then from there, we are going to be consuming those events. And this gives us a lot of functionality out of the box. It gives us data retention, which is kind of the most important part. So if like our nodes that are consuming these events, somehow they crash, well, then they can pick up where they left off, and they can also reconsume the events that they previously had. And also that we can consume these events asynchronously. And at a high level, we know like something is going to go on here. Something is going to take these events. It's going to consume the events and it's going to aggregate them. And then somehow we're going to have to like do the time windows as well. But for now, we're kind of ignoring that. We're focusing on just like the all-time solution. So we'll aggregate all the events. And at some point, there's also going to be a client involved, and they're going to be probably going through some kind of API gateway, which is going to hit some server, which is probably going to hit some database or some kind of storage sink where we are actually storing those top K songs for the given windows that we are making available to people. Now, the question is, how are we going to be doing this? So filling in basically everything that's going on here. And there's actually two solutions that I want to talk about. One is kind of an out-of-the-box solution. We're going to be talking about Flink and how it has a lot of built-in functionality that can help us solve this problem in a pretty straightforward way. There are going to be some details on how to like scale it and stuff like that, but it's mostly a straightforward solution. We're also then going to be covering more elaborately the other solution that doesn't involve Flink, and it just involves like our own servers, possibly some workers that are aggregating the data. I'm going to very quickly cover this solution. I'm also going to do a quick demo of Flink, just a really simple one. By the way, if you don't know Flink or you're not familiar with data processing, as you might not be, definitely check out System Design School. Promise you won't regret it. So let's quickly jump into that Flink demo. Here is about 100 lines of code, I think. Yeah, about 100 lines. And it's a relatively simple example. It looks more complicated than it is. So let me kind of just briefly go over it. It's Java, just because I think the types are going to be helpful here. Could have used Python as well, but a lot of imports. But most importantly here, we have our window aggregator class, which is extending a Flink class, the window function, because we are going to be solving this problem with windowing. That's what Flink can do for us. It can do that out of the box. So this is a really simple, just kind of local demo that I'm going to run for you after we kind of just briefly go over the rest of the code. For top K, we just have a variable 5. We're just going to maintain the top 5 values. And so we have a couple of functions here. One, the main function, which is just setting everything up and then executing the process. And we have our function over here, process, which overrides a Flink function. And this is where the bulk of the logic is actually going to live. So up above here, we have to be consuming data from somewhere. And rather than setting up Flink locally, I'm just keeping it really simple and opening a TCP socket on port 9999. And locally, I'm going to send messages to that port. And next, we're mapping the input and just transforming the data into tuples, where we get the item ID, in this case, the song ID, and the second one is the count, which is just going to be 1 initially. That's why we kind of hard code that here. Next, this is the interesting part where we have the windowing logic. Pay most attention to this line over here because this determines the first parameter here determines the size of the window. So for example, if we wanted the top K songs in the last minute, this is what we would do. If we wanted the top K songs in the last hour, we would put 60 minutes here. So that's what this is doing. Now, what is the second parameter here? Well, that's going to decide how often our sliding window here is going to shift. So that's why it says sliding window here. We could have done a tumbling window as well, but we didn't. We did a sliding window. That's why we have the second parameter here, which is going to tell us every 5 seconds is when it should emit a value. Every 5 seconds is when we want a value. So this is just creating that top K stream. After that, we have some printing logic and we actually execute the Flink job. Now in the processing logic, this is where we're receiving the actual messages and we're just iterating over all of them and counting them pretty simply in a hash map down here. And keep in mind that this function here is going to emit every 5 seconds, but the data that it's going to keep track of within the window, within the state. So Flink is stateful. It manages its own state. In our case, we're just managing the state in memory with a hash map, but we could have done it differently. And so that logic will ensure that the counts are for the last minute in our case. So you can see that a lot of this really does come out of the box with the Flink. That's what I'm kind of trying to illustrate to you with this example, that most of today's system design interview question can be solved with Flink. Now to actually get the top K counts, we will use a heap, specifically a minimum heap. You might be wondering why that is. We're going to cover it more in depth later on, so I'm not going to go too in depth here. Ultimately, at the end, we push the elements out to the output collector, sorry. By the way, I heavily used AI to generate a lot of this code, as you can probably tell, and I would encourage you guys to do the same. It's pretty easy to play around with it. So now let's actually go ahead and run this little demo. And like I said, I'm going to be opening up a TCP connection. So on port, I'm using Netcat, by the way, on port 9999. Before I send any messages here, I'm going to also on the other tab actually run our program with that little command and giving it a second. That was pretty quick actually. So it switched from initialization to running. And that happened multiple times because there's actually multiple subtasks running with Flink. So I'm running this locally on my one machine. So it's not like this is distributed, but there still is a lot of concurrency going on. So when we actually start sending some messages, that's when things are going to get interesting. Let me just make this a little bit bigger. And so I'm going to send hello, and pretty shortly after, within 5 seconds, we should see a message on the left side. Yep, there you go. We should see it again within 5 seconds. Yep, there you go. We saw it again. And by the way, this number 7 means that that is like sort of like the thread that Flink is using. I believe the correct word is subtask. But let's send in another word. So I'm going to type in hello again. Now, when a minute passes, well, giving it a second. Okay, so now we see hello has a count of 2. If I send in a different key, I don't think it's going to be 7. I think that key is going to be sent to a different sort of like subtask. So let's try that. Let's send in world and world one more time, and maybe even just hi. So let's see what happens now. Okay, so we saw some debugging logs, but we see hello has a count of 2, hi has a count of 1, world has a count of 2. And that was from 13, that was from subtask 7, subtask 9. Now, once a minute passes, we should see these counts start to reduce. Which count do you think is going to go to 0 first? Probably hello, because that's what we typed in first. And you can already see it. Now hello is 1. Within a few seconds, we'll probably see it back down to 0, or probably just not showing up at all. Okay, so some time passed, and now I think we're done with the hellos. They are no longer a part of our window. So we only see world equals 2, hi equals 1. After a few more seconds, those should go down to 0 as well. And yeah, now we are not getting any more print statements executing. These were the last ones, and I'm pretty much done with this now. You can kind of see the power that windowing provides within Flink. This pretty much solves the problem for us. Not only does it solve the all-time problem, because we could just have a hash map that keeps track of the counts, and we wouldn't really need any of the windowing logic. So this example isn't really the all-time example. This is the example where we're just looking for maybe the last hour, the last 24 hours, the last month, something like that. And you might think, well, how is it going to store all that data in memory? Well, it doesn't have to store it in memory. Flink does provide some persistent ways to store data as well. But even so, we could just write the data that's coming out of Flink to some kind of sink, like a database or Redis, and that pretty much solves the problem for us. So let's go back to our diagram. So at a very, very high level, we see that we have our Flink instance here. It's going to be aggregating the counts, which is straightforward enough. So for every song ID, we can just keep track of the counts. We could use a hash map, we could use a database, doesn't really matter too much, as long as that data is being written to some sort of sync. And in our case, probably something like Redis will be sufficient, because then we can update that Redis periodically. So for every every minute that passes, Flink can then send the data to Redis, store the top K 1000 songs, and then we can read from there as well. If we want to scale these reads, it's pretty easy to do so with just some replicas, so that's not really the complicated part. There is also going to be some scaling that's going to be going on here as well, which I'm not really going to talk about right now, because scaling this is going to be very similar to scaling the other solution I'm going to talk about. So I'll save it for that. But one thing I kind of glossed over is, how do we actually get those top K elements? I showed that heap, that min heap in Flink that we had. That's something I'm actually also going to talk about in the other solution. So I'm not going to go super in depth here, but the main thing I wanted to get across with this solution is that this is a working solution. Sure, there are some scaling needs that need to be addressed, but absolutely, we solved the problem of all time. We solved the problem of getting all the songs within the last month or last hour, and we solved that with the windowing capabilities of Flink. Okay, so now let's try to find a working solution without Flink, and it's going to be pretty similar conceptually. Instead of having Flink here, let's say we have a bunch of workers, and they're going to be doing largely the same thing that we had in Flink, in the sense that we're going to internally maybe have some kind of hash map which keeps track of the counts. So let's stick with the example of like all time counts, because it's going to be harder to do the window solutions without Flink. So that's going to be the challenge here, handling those. So okay, it's taking those messages that are coming in, just keeping the count of them. So based on like the song ID, we'll have a count. Now, how do we then take those and then get the top K? How do we get the top 1000 songs? Because hash maps are not sorted, of course. Well, that's where the heap data structure is going to come in. And this is kind of like a data structures and algorithms problem. We're specifically going to be using a minimum heap. And the reason for that is more simple than you think. We don't want the minimum counts, we want the top counts. So why do we use a minimum heap rather than a maximum heap? Because we want everything within the heap to be the top counts. So if we see, like, let's say our heap now is 1001 elements. Or to make it simple, let's say it's 1000 elements, so it's at capacity. And now we just got a new song that just came in. And this song now has a count that is larger than the minimum value in our minimum heap. So what should we do? Well, we should pop the minimum value from the min heap, and we can do that because it's a minimum heap. If it was a max heap, we wouldn't be able to pop the minimum. After we pop the minimum, then we can just take this count and then push it to the heap, because we know at the very least it is within the top K. And we know that within heaps, like, the values aren't sorted, but we could sort that pretty easily. Once we have the top K, it's pretty easy to just sort 1000 elements. That's not really the hard part. The hard part is taking all these songs, there could be millions and millions of songs, and then only getting the top 1000 of those. Now, I'm pretty sure 90% of people wouldn't notice this, and your interviewer most likely wouldn't as well, but I think it's still worth mentioning. How do we make sure, like, we have a heap, a min heap, and we have a hash map with the counts. We expect that a song with a certain count, when it's pushed to the heap, or if it's already within the heap, the count of it should be accurate. Now, how do we do that? How do we update a value in a heap? That's not typically what heaps are made to do. Well, that's something that's easily we can work around just by having a hash map which will keep track of the index of every song ID that's in the heap. That way, not only can we update the count in the heap, but also we can check if a song comes in and now it has a really high count. Well, maybe it's already a part of the heap. We don't need to push it to the heap again. We don't need to pop somebody from the heap just to add this, because it already exists in the heap. I just thought that was worth mentioning. But more importantly, with this solution, even though it seems like a working solution for the all-time counts problem, which it somewhat is, it does have a couple notable drawbacks. Those drawbacks are, one, we have a single point of failure, which is somewhat trivial to get around, but there's some subtle things that are worth mentioning that I'll talk about. But also, maybe more importantly, the throughput of the system. How do we make sure this system can handle 10 billion songs played per day, which roughly would come out to, I think 10 billion is 10 to the power of 10, And I think we have roughly 100K seconds in a day, which is 10 to the power of 5. So we might have something like 100K events per second. Quite a lot. So now I think we're pretty much diving deeper into some of these scalability issues. And I think probably the other thing worth addressing with this is also, how do we actually handle those windows like last hour or last month? So let's go through these in order. For the single point of failure, I think it's typically the case that we just replicate our service. So we'll have a replica that is doing the exact same thing. And just to illustrate that, I'll just create a few more boxes that will be like slightly overlapping. Now that we have replicas, what happens if one of them goes down and we need to replace the replica? How do we create a new instance of these workers? Because the data that's coming in might not be there anymore. So for example, if I'm going through like the all-time example, I want all the top songs from all time, and now I need to set up another worker. Well, where is it going to get all of the data from? Are we expecting that our Kafka instance has retention for literally every single message that it's ever going to receive? Because that's going to be quite a lot of songs played, and it's just going to keep growing and growing. So we probably want to have a limit on that Kafka retention. By the way, if you're not familiar with like what I'm talking about, Kafka and stuff, this is probably a good chance to maybe head over to System Design School, skim through the primer, consider checking out the course if you have purchased that. But conceptually, it's a pretty simple concept. Kafka is, in some cases, kind of like a database in that it can retain data. And I won't go down that rabbit hole of like how Kafka is a database. It's not necessarily a database, but anyways. We could set some kind of retention period, like for example, the last 24 hours or the last 3 days, something like that. So it will have all messages saved for that period of time. So if we do set up another instance of our worker, it can then read through those messages. Okay, but then we don't have all of the data, the all-time data. So what should we do? Well, it's pretty simple. Periodically, we could just snapshot or checkpoint the data in some kind of database. So I'll just put like checkpoint here, or maybe snapshot is more descriptive, but we could snapshot the data. So whatever the all-time counts were at a certain point in time, we'll periodically snapshot those. And that way we can set the retention on Kafka to be less than all time. So then when a new worker is set up, it'll just read all of the data from here and then start consuming from a certain offset. So whenever that snapshot was created, it'll start reading from that offset within the Kafka stream. Now, for throughput, the typical solution is to partition or shard our service. So with Kafka, we might actually be able to handle 100,000 requests per second, but this could have been a bigger number, or maybe our interviewer just wants us to go down the more interesting solution. So what we can do is partition our Kafka instance, and we should probably do that by the song ID. And the reason for that is because now we're trying to scale our service horizontally. We know that a single worker probably isn't going to be able to handle 100,000 requests per second. So not only are we going to partition Kafka, we're also going to partition our workers such that each of them is only going to be responsible for a subset of the IDs, because the whole thing that we're trying to do here is get the top K songs. If we mix up songs, like one worker has the same song as another worker, we might be able to do that, but it just doesn't make as much sense to do that. Okay, so now not only are we going to replicate our services, but we're going to partition them based on the song ID so that each Kafka partition will be responsible for a subset of them, and then those subsets will go to a certain worker. In terms of how many partitions we would need, probably roughly 100 would be sufficient, I would think, for this type of scale, but anywhere from like 100 to maybe a couple hundred would likely be enough, and possibly even far less than that. But now that we have our partitions, let me kind of draw them first. So I've updated this diagram a little bit, and I'm not going to draw every single arrow. I'm not going to draw an arrow from here to here, but can you see something that's wrong here? I'll give you a hint. It's in this general area. If I say, for example, that this worker is maybe responsible for, just to keep it simple, let's say song IDs from 0 to 99. And more realistically, we might do some kind of mod math. So let's say if this has a remainder of 0 after being modded by some kind of prime number. But I'll leave it simple. Let's say 0 through 99. And then the other one is maybe 100 to 199. Well, now we have to ask ourselves, what are we doing with the data? If this guy has the top K songs from just a subset of the songs and we're writing that to Redis, I mean, that's fine, but then we're writing another subset to Redis as well. So now which one is the user going to read? Well, we have to somehow combine those. So we can create another service in between here, which is going to basically be solving that leak code problem of merge K sorted lists, because now we're going to have multiple heaps and we're going to have to merge those heaps so that among all of them, we get the top K songs. So we're going to have a top K service, which is going to be responsible for reading. Either it could directly read from the workers somehow, or those messages could be pushed to the top K service, or maybe the workers could alternatively just send the data to Redis, and then the top K service could fetch that and then do the aggregation, combining them and then getting the top K from them, and then writing that back to Redis as well. So this is something that should be very much feasible. So we've actually covered pretty much everything, I think, when it comes to the non-functional requirements. We're able to handle the throughput. We have a large number of songs, which is fine. We can partition to handle that. The latency should be relatively low, and we are able to do that, I think, just because the client is going to be reading from Redis, and that's going to be pretty fast. And we're updating Redis in real time. So periodically, maybe every 60 seconds, we will be getting the top K from each and then updating that. That should be a pretty simple operation. And it should be fast because we've done partitioning at this layer. And since we're updating this every 60 seconds, we can expect that the latency for a song to be included should be close enough. But we're not handling the window part of this. So the last part is going to be that. And conceptually, it's actually pretty simple. It's similar to data structures and algorithms once again. Think about what we're trying to do here. We have, let's say, this timeline of events that are coming in. And on the right side is the current time. If I want only a subset of the events, let's say the last hour, what I'm basically saying is I want to not include anything that came before that. So that's the only difference between this and the all-time solution. Now, the question is, how exactly do we achieve that? Because this is, like, conceptually, it's just a sliding window. That's all we're doing. All we're saying is keep collecting everything that's coming in right now, but don't collect anything that came before that last hour. So remove everything that came before then. So, and as time passes, as we add more data here, we're going to say remove this part over there. So the time that each song is played is going to matter because that's going to allow us to determine that a song play is no longer relevant for our current window. We saw that Flink was able to handle this out of the box, but how can we implement that solution ourselves, sort of from scratch? Well, thankfully, we don't have to go all the way from scratch. We can take advantage of the capabilities of Kafka. We can have multiple pointers in our Kafka queue. So to review the all-time solution, we only need one pointer because we don't have a window. I mean, we kind of do, but the window is unbounded. It's just all time. So I guess it's not really a window. So we only need one pointer. We just need to read the most recent message that comes in. But for the other solutions, like for the last hour, we're going to have not only the most recent pointer, we can probably just reuse the pointer for the all-time solution as well. We can probably reuse the same pointer that the all-time counts are using, but we'll have a second pointer with an offset of 1 hour from the current time, which is also going to be reading messages. Now, when we read these messages, we're not going to add them to the hash map. We're going to remove them from the hash map. We're going to decrement the count of the hash map for that particular window. So let's say that we have a bunch of hash maps. So we have a hash map for every single top K that we're looking for. So we could have a hash map for the all time. We could also have it for the last hour. We'll have a separate hash map for each. And each of those hash maps will keep a count. And we'll also then have a separate heap for each of these as well. Now, there's going to be a decent amount of logic to actually handle that, to make sure that that second pointer doesn't actually get close enough to the other one. And if it ever does get close, then we'll stop it. We'll pause consuming from the Kafka queue, which is something that we can do. But again, that is going to be some extra logic that we're going to have to add to our workers, whereas we were able to solve this problem with Flink much easier. By the way, if you were wondering how I was going to scale the Flink solution, it was going to be pretty similar. We were going to partition that horizontally based on song ID. We were also going to be doing some snapshotting, but I don't think we would need snapshotting. That's something that Flink can also take care of. So with that, we're able to handle this last case as well. And by the way, if you're wondering again, like how that stuff is going to work under the hood, the hash map and the heap stuff, the hash map is pretty easy to update. The heap can also be updated, but there is going to be some reheapifying going on. For example, if we had a heap that looked something like this, maybe with a root of that, and let's say this is a min heap, by the way. So there was that, and then there's like a 5 over here. Let's say we took this count and we updated it. We incremented it to be some big number, let's say 13. Well, now this is no longer a heap. Well, how would that work? Internally, we can just have our own implementation of a heap, and then we can just percolate this guy down. Every time we make an update to the heap, we can do sort of that reheapifying, which should be pretty efficient given that the heap isn't going to be larger than 1,000 anyway. So even if we did have to iterate over every single element, it wouldn't be too bad. But it won't have to iterate over every element. It'll just go through the height of the heap, which should be log k, where k is whatever the parameter that we're talking about is. Anyways, I really hope you guys enjoyed this video. It took me multiple days to record. That's why I'm wearing a different shirt now, and I probably look a little bit different. But thanks for watching, and I'll see you soon. And definitely check out System Design School for the full write-up and to learn a lot more.